Good day to the panel of judges. Today, we, USM Go, consisting of PRAVEN, KAVILAN, and FAZLAN, supervised by Associate Professor Dr. Thian, will be presenting the green steam cracking furnace, hydrogen versus electricity. Right now, we will go through these 4 sections in this research to completely understand the differences between electrical furnace and hydrogen-fueled furnace. So we will go through introduction and literature review first. Second will be hydrogen-fueled furnace. And third will be electrical furnace, and fourth will be analysis of both of the furnaces. For the first section, we will understand the importance of this evaluation that has been conducted and the current available technologies. As we know, crude oil is the source of naphtha, and naphtha is the imported chemical used to produce 80% of global demand of ethylene and 60% of global demand of propylene. Ethylene is expected to increase from 176 to 287 billion USD within the year of 2021 to 2030. Whereas the increment of propylene demand is from 94.67 to 135.21 billion USD from the year of 2021 to 2029. Both of these increment will cause the increase in the environmental concern that is already existing, which is the production of 1 to 1.8 tons of carbon dioxide for 1 ton of ethylene production. As mentioned earlier, the environmental concern causing us to conduct this comparison research of electrical furnace and hydrogen-fueled furnace. But first, we must understand the conventional steam cracking of naphtha, where there are 3 sections, which are first, pyrolysis, where naphtha is cracked and quenched in TLE. Second is primary fractionation, where gas fraction is quenched again and undergoes multi-stage compressor and removal of unwanted substances. And lastly, product recovery, where products are distilled to separate ethylene, propylene, and other components. As we know, hydrogen can be used as a replacement for the fuel in the furnace, which is normally natural gas. So therefore, this area shows that all the hydrogen production that are available currently, and we have chosen to explore the hydrogen water splitting, which is thermolysis to be exact. Electrical furnace is fairly simple in operation because it is just a replacement of fossil fuel with electricity derived from solar. The rest of the naphtha cracking process is very similar to the conventional method. This is the base case of naphtha cracking simulated in Aspen Plus. The naphtha properties utilized here is given from the question itself. There are certain assumptions that has been done here, where it is steady state operation, negligible pressure drop in piping, no heat loss to the surrounding, naphtha to steam ratio is 1.33. The naphthene and the aromatic in the naphtha is assumed to be cyclopentene and toluene respectively because there are lots of aromatics and lots of naphthene, and we do not have the detailed data for it. And after the simulation has been done, the obtained required duty for this base case is 18,500 kilowatt for that 18 ton of hour of naphtha cracking with the production of 14.4 ton per hour of steam.
Hello, I'm Praveen here. For the next section, we'll be looking at hydrogen-fueled furnace, and this is done to understand the concept of hydrogen-fueled furnace. This is the thermolysis flowsheet. As you can see, this is the process description we used in Aspen Plus to design the hydrogen fuel that is required to be used in the furnace for cracking later on. So in designing the thermolysis of water, we have made a few assumptions. The assumptions are proton exchange membrane is within a stoichiometric reactor. No heat loss or enthalpy loss in the entire system. The conversion is assumed to be 90%. 100% of the hydrogen, oxygen, and water is separated. The reactor operates in ideal condition. Distilled water is used for the splitting process, and ambient pressure is set to 1 atm for the entire process. And heat is obtained from solar cell. The simulation is shown previously in Aspen. The process description can be split into 4 sections. The first one being a reaction system, followed by a heat exchanger network, and then a separation, and lastly is the usage of the hydrogen in the furnace for cracking process. And lastly, for hydrogen production would be determining the solar panel surface area used for the hydrogen production. Taking the yearly average value, the worst case scenario is at Ching, where it's only 1,470 kilowatt hours per meter squared. We require approximately 27 million meter squares of solar panel, and each of these solar panel generates around 8.96 kilowatt hour per meter squared, and the polycrystalline solar panels average around 5.34% efficiency.
Now let us look at the next technology that we can employ for naphtha cracking by using electrical furnace. This section is to give an understanding of the concept of electrical furnace. Before going further, let us have a quick glance on the methods to generate the electricity. There are a few different methods that we can use to generate electricity. However, the hydropower, solar power, and wind power has the least amount of CO2 emission to the environment to produce the electricity to be used for the electrical furnace. So for this electric route of naphtha cracking, we will be using electricity from solar power. So once we have identified the electric production route, now let us look at the furnace technology that can be used to crack naphtha by using electric as the energy source. There are few types of furnace that can be used to supply heat, which are the first one is the induction heating, second is the electric arc furnace, third is infrared heating, plasma heating, microwave heating, and resistant heating. All of these type of furnace have its own pros and cons, for example like the efficiency of it. So for this case study, resistance heating type of furnace will be used since it has the highest efficiency as compared to the other type of furnace. Previously, it has been mentioned that the electric production route selected will be through the solar technology. For this electric production through solar technology, the surface area of the solar panel can be calculated by taking the yearly average solar radiation value for Kuching, which has the least solar radiation as the worst case scenario. The estimated surface area of solar panel is estimated to be 2 million meters square, where the average module efficiency is taken to be 5.34%, so meaning that each meter square of solar panel, the energy produced is 8.96 watt. So now we have the understanding of both type of furnace to crack the naphtha. Now let us compare and analyze both furnace. This section outcome is to give an understanding on the costing, environment, and safety impact, operational and equipment challenges, and potential improvement. First, for the costing, as can be observed from the table shown, the electric furnace is having a total permanent investment of 500 million USD per year, whereas the hydrogen fueled furnace having a total permanent investment of 5 million USD per year. For the electrical furnace, the working capital and utility costs are zero, whereas for the hydrogen fueled furnace, the working capital is estimated to be 2 million USD per year and the utility cost is estimated to be 55,000 USD per year.
Now, I'm going to present about the sustainability of the designs of furnace, safety consideration, operational challenges and equipment requirements, and potential improvements which can be done for better performance of the furnace. So, in sustainability of the design, there are mainly four categories which are analyzed for the design. First is entire carbon footprint, energy efficiency, waste produced and its management, and the renewable resources. So as for the entire carbon footprint from the both furnace designs, for the hydrogen fuel furnace, zero carbon emission is found in terms of operation due to no fossil fuel. Manufacturing of solar panel and equipment will be the only contribution for carbon emission. Same goes with the electrical furnace, where it is also considered zero carbon emission in terms of the process, and also the manufacturing of solar panel is the main contribution for the carbon emission. Energy efficiency wise, both hydrogen fuel furnace and electrical furnace has similar percentage, which is 5.34. For the waste produced and management, for hydrogen fuel furnace, unreacted water is recycled and the spent cooling water is used as steam for the furnace cracking. And then for electrical furnace, no hourly waste is produced in the operation of producing electricity. Only disposal of solar panel after useful life is present. Then for the renewable resource, for the hydrogen fuel furnace, thermal energy is produced from solar based electrical energy, while for electrical furnace, electricity is produced from solar energy. In safety wise, the hazards involved and the possible mitigations are addressed in this section. For hydrogen fuel furnace, the main hazards found are flammability, explosion, embrittlement, and also corrosion. This is because hydrogen is considered as flammable and potentially explosive under high pressures, and also hydrogen in metal pipes can cause embrittlement and corrosion to the pipes. Meanwhile, for the electrical furnace, some solar panels will contain toxic substances such as lead, cadmium, and heavy metals. And if any leakage happens, and if it mix with the environment, it will be hazardous to the human health and to the environment. Other than that, the possible mitigations involved in the hydrogen fuel furnace are mainly divided into three parts, which is high flow rate, high temperature, and what if excess electrical energy is found. And then for electrical furnace, electrical hazards, high temperature, and also excess electrical energy. So for the hydrogen fuel furnace, high flow rate are present, therefore operators have to ensure that proper material are used in construction of the water storage tanks and the subsequent hydrogen containment units. While for high temperature, the high temperature required for the process for splitting water needs to be considered when designing and operating the plant. Other than that, excess electrical energy in the solar panels do carry a high voltage and must be handled with care, especially in the huge area required for this process. For the electrical furnace, electrical hazards are present, therefore operators are provided with electrical charge protection attire and safeguards such as warning are presented. High temperature is possible to be achieved in the electrical furnace, therefore temperature monitoring is essential. Excess electrical energy are eliminated by grounding and lightning protection and override protection device. In this section, operational challenges and equipment requirements are addressed for both the hydrogen fuel furnace and electrical furnace. There are several operational challenges in hydrogen fuel furnace, such as variability of solar resource, intermittency, energy conversion and yield, control system for hydrogen production, maintenance of equipments, and land use and optimal direction. While for the electrical furnace, it is similar to the hydrogen fuel furnace, but the regular maintenance are required for the electrical furnace, and also technological advancement is another operational challenge comparing to the hydrogen fuel furnace. For equipment requirements for hydrogen fuel furnace, solar panels, which is photovoltaic modules, mounting system, DC to AC inverter, wiring, monitoring system, unit operations such as reactors, heat exchangers, and furnace, separation unit, mixers, and piping systems are required for the hydrogen production. Meanwhile, for electrical furnace, the unit operations and piping systems are not required, but it required battery instead of these two systems. In this section, potential improvements which can be made for the hydrogen fuel furnace and electrical furnaces are found. For hydrogen fuel furnace, reactor and heat exchanger designed with multiple stages in single unit can be used for reduction in operation units used in the plant. Other than that, usage of different materials for solar panels to improve the efficiency can be used. The utilizing steam produced from heat exchangers can be used for cracking process. The heat integration can be done for reduction of heat losses in the plant. Meanwhile, for the electrical furnace, utilization of different material for solar panel can be done to improve its efficiency. Exploration of thin film technology to save material and costing from solar panel can be done. Other than that, implementation of concentrated solar power technologies can be done to improve the efficiency of the electrical furnace. Lastly, using solar tracking to maximize the solar radiation absorption is also another potential improvement which can be done in this electrical furnace.
Now I would like to explain the conclusion which summarizes the key findings and the recommendation to the decision makers. As it can be seen from the key findings, for the thermolysis of water, it has high energy requirement, it has zero carbon emission, but the large area of solar panels is a concerning situation, more equipment causing higher maintenance, more safety concern due to the hydrogen. Comparing them to the electrical furnace, it has no waste production at all, zero carbon emission, but similar case to the thermolysis of water, it has a large area of solar panel, cheaper compared to the hydrogen production. No handling of chemicals are required because there is no chemical being produced and there is no requirement of piping infrastructure. Recommendation to a decision maker is that both type of furnaces have extreme capital costs with no carbon emission, yet the electrical furnace is better due to the no waste produced and chemical being handled. The safety concern is also less and requires lesser maintenance. Improving the efficiency of the solar will reduce the area of the solar panel, or utilizing hydropower will cause the electricity generation to be more efficient, and it can be a feasible option but not in all areas. So that is an option up to the decision maker when it comes to the area where they want to build the naphtha cracking plant with the electricity generation. And that is all for our presentation. Thank you for listening to us and have a nice day.